Ladies and gentlemen, please welcome Eric Starkloff.
All right. All right. All right. Good morning, and welcome to the largest NI Week ever by a long shot. Over 3,400 attendees. Give a hand for that. We have an amazing week planned for you, and I'm so excited I can hardly contain myself, and we're going to have a little fun kicking it off here this morning. It's been amazing to see the growth of NI Week over the years. This is our 18th annual conference, and it started as a small user conference back in 1994, and it's grown to become the preeminent system design conference in the world. Now, over this same period of time, NI's done a little bit of growing too. Since we last saw you, we hit a milestone of over $1 billion in annual revenue. So NI employees in the room clap. We've grown to over 6,500 employees, and probably most importantly to all of you in the room, we've continued to invest aggressively in R&D. Last year we spent over $200 million in research and development. And this morning, myself, along with some of our leaders from engineering and marketing, are going to show you the fruits of that investment, some of the most exciting products we have ever launched, and we can't wait to show them to you. Now, National Instruments has built our strategy leveraging another exponential curve as well. It's the one predicted back in 1965 by Gordon Moore of Intel, and known throughout the world as Moore's Law. Now, Moore's predictions have continued to hold true. And since 1976, when National Instruments was founded, the number of transistors on a microprocessor has grown by a factor of 400,000. And computers have changed dramatically over our lifetimes. The increase in performance has been coupled by equally impressive decrease in size, power consumption, and cost. It's estimated that building today's iPad out of 1976 transistors would cost $3.2 billion. It's an amazing stat. And at that same period of time, though, traditional instruments haven't kept up the same pace. Here I'm showing you the state-of-the-art spectrum analyzers over these decades. And they basically look the same. I mean, their RF performance has increased some, and they got better screens, but at nowhere near the pace of increased performance that the PC saw. Now, National Instruments was founded on the premise of changing this, of taking this rapid innovation from commercial technologies and bringing them to measurement and control applications. Now, there are two implications of Moore's Law that are talked about a lot less than the exponential performance increase that it predicts. The first of which is software. You know, what we've done with all of this increased processing power is we've used it to run increasingly powerful and sophisticated software. Everything in our lives now is software-centric, from our automobiles, our infrastructure systems, our appliances, and of course our smart mobile devices. And the amount of software in these systems has really exploded. Some luxury cars can have up to 100 million lines of embedded code. It's a staggering amount of complexity. Clearly, we cannot continue to design and test these systems at the same low level that we once did. We need a fundamentally different approach, one that abstracts that complexity to the system level so that you can design and test at that system level. Now, when you're designing at a system level, you can allow people with expertise in a particular domain to design exactly the system they want without the need for specialists. I was thinking of this issue just a few weeks back, and I was using the analogy of a home improvement project. So I'm in a room full of engineers, and I'm guessing that a few of you have used Google SketchUp. It's a little project that I did not too long ago. And when you're a homeowner and doing home improvement, you are a domain expert. You know exactly what you want. But in the past, something always gets lost in the translation between what you want, what an architect designs, and what a builder builds. Now, it turns out there's a lot more domain experts in the world than there are specialists. In this home improvement analogy, For example, there's over 100 million homeowners in the US, and only about 90,000 architects. Now, to use an example that's a little bit closer to home, there's only also about 100,000 HDL developers in the world. These are FPGA programming specialists. And yet there's over 10 million engineers. And we fundamentally believe that all of those engineers should have access to technology like an FPGA to use it to improve the performance and cost of their systems. Now, we all know that Moore's Law doesn't come for free. It comes with a tremendous and focused investment. Intel, for example, invests billions of dollars every year in the process technologies to keep them on the curve. And this brings us to the second implication of Moore's Law. It takes a focused and intense platform on a single common platform. If Intel had 50 different processor architectures, there's no way they could scale this investment to keep themselves on that curve. And now we're seeing the rise of another company with a very intense platform focus. Apple has been able to disrupt computers, televisions, mobile phones, and publishing with a single platform. And they've been able to build compelling products while reducing the cost of those products and scale the functionality of them exponentially over time. They've also shown us another important benefit of a common platform, and that's the development of an ecosystem. There are now over 650,000 apps in the App Store, and that combination of a robust ecosystem with a common platform has become a powerfully disruptive force in the applications that they serve. Now, all of you at NI Week are system designers. You're designing all different types of systems, an amazing spectrum from measurement systems to high-performance test systems to embedded control systems. And I think one of the most unique things about NI is that we view all of those different applications along a continuum. They're made of the same building blocks of hardware and software. And we call this approach graphical system design. Now, the fact that a single platform serves all of these different domains has a real benefit to the system designers that use it. You might not have realized, for example, if you're an RF test system designer, that you could benefit from including closed-loop control technology into your test system. But we're going to show you exactly an example of that later in the keynote. As an embedded system designer, you might not have realized the benefit of instrument class I/O in your embedded system. Well, we're going to show you an example of that as well. Now, at the heart of our platform is LabVIEW, and its combination of graphical development combined with multiple models of computation to map to these different application spaces has proven to be unparalleled as a system design language. And so as we go through this journey this morning, talking about these different applications and showing you some of the amazing new technology that NI is releasing to serve them, I couldn't think of a better place to start.